Harsh, any doubt?
No, sir. Sir, what was the answer for first, second, and third?
Second, we have to calculate temperature gradient.
Yes, sir.
So temperature gradient means change in temperature with respect to change in length. That means you have to calculate delta T divided by delta
By
L.
delta L, right?
So delta T, the total temperature difference at across its end, and delta L for that part we have
Change
50
of
centimeter.
Yeah, 50.
That is 0.5 meter.
Yes, sir. Sir, is the second one 200? Like the answer?
Yeah,
It's 200, right?
200.
Okay, sir. Got it.
You got third one?
Sir, for the third one, the formula is delta Q by delta T, right?
No, we have to calculate thermal resistance. Thermal resistance is L divided by K into A. Length we have 0.5.
0.5. K is
Thermal
0.8.
conductivity and area of cross section of this part.
Okay.
So it will be 0.1 multiplied by 0.1.
So, sir, I just used the wrong formula.
Okay. So it will be 5 by 8 into 10 to the power 2. That is 500 by 8. Is it clear?
Yes, sir.
Tell me the formula of heat current according to Ohm's law. Current
According
is
to
simply
Ohm's law,
equals to voltage difference by resistance.
voltage by resistance.
So
Yeah.
in terms of voltage, in this part, we have temperature difference. So it will be delta T divided by R.
So can you hear me?
Yeah.
No, sir, I'm just telling the formula. Like I thought I was disconnected. So
Okay.
it's voltage by difference, right?
In last class, I defined you how to calculate this one. H is equals to delta T divided by R. That is temperature difference divided by thermal resistance.
Thermal resistance, yes.
So heat current will be equals to delta T divided by R. We have calculated delta T in first part and resistance in third part. So you get amount of heat current in this particular time gap.
Yes, sir.
Next is amount of heat reached to the other end in 1 minute. So according to formula, H is equals to Q divided by T. So we have to calculate Q. So it must be equals to H into T.
Yes.
H we have calculated in fourth part and time taken in this part we have 1 minute.
1 minute. 60 seconds.
That is
60
seconds. Next, in last part, we have to calculate amount of ice melted during this particular time. So on reaching this much amount of heat to the other end, we're capable to melt some amount of ice. According to the formula, Q is equals to mass of ice to be melted times latent rate of fusion constant. So you get mass of ice to be melted by this much amount of heat. Is it clear?
Yes, sir.
Any doubt?
No, sir. Like,
okay.
1 minute, sir. 1 minute.
Okay, just write it down.
Yes, sir. Sir, I wrote the formulas already. Like, I had
okay, good. Next is temperature of junction.
So can I scroll it up for 1 minute? Just 1 minute, sir. Oh, okay, sir. Yeah. Just checking the figure.
Next is temperature of junction. Suppose you have a rod and another rod. Let's say temperature of this end is 100 degrees Celsius and this end is 20 degrees Celsius. We have to calculate this particular temperature of junction. Let me give you some values. Thermal conductivity of this rod is 0.5 watt per meter per Kelvin. Thermal conductivity of this rod is 0.3 watt per meter per Kelvin. Length of this rod 0.8 meter and length of this rod 0.4 meter. How to calculate temperature of junction in this part?
So like we have to subtract the higher to lower or something like that?
No.
Okay.
In this part, we have two different rods having different thermal conductivity. So you must say there will be some flow of heat current from higher temperature to lower temperature in this part. So it will be H1 is equals to Ka by L times temperature difference 100 minus T naught. Let's say area of this particular part is twice of that of this area. So heat current in second part, we have Ka by length, temperature difference T naught minus 20. Now try to guess this particular combination. Is it series combination or parallel combination?
The parallel, sir. No, sir. Series.
And in series combination, we will have same amount of current through each different resistor. So we can say, since it is in series,
then we can add, right?
so we can equate H1
Yeah,
and
we can
H2.
equate. We can equate. Yeah.
So on equating, you will get T naught, that is temperature of junction. Any doubt?
Okay. No, sir.
Just write it down and try to simplify for T naught.
Okay, sir. Sir,
Yes.
like, sir, in a school that did deleting some portion for the exams because they're not able to complete, and I don't think we studied this, so it's new to me.
Okay.
Yeah. This and I guess some, so like last, not like in this chapter only, some like later need fusion constant. These were not there in my like portions.
Okay. So tell me the topic which you have been out.
Sir, I have to check my notebooks. Sir, like I'll study this because this is important, but they're deleting some topics.
Okay, no problem. So we may skip this particular part.
Okay.
You have learned radiation, Stephen's law, Kirchhoff's law, Newton's law of cooling, these things.
Sir, I'll just check my notebook. So 1 minute.
Okay, just one.
I guess we have to one minute, sir. So yes, sir. We have done Newton's law of cooling, black body radiation, and Wayne's law, Stephen's law. We have done. Sir.
Okay. So let's start radiation.
Yes, sir.
First, what do you mean by radiation? Any idea?
So like heat is transferred.
Okay. You may call it radiation is a type of electromagnetic wave. Do you know electromagnetic wave?
Yeah, so like I don't know the definition, but I just know it like that.
Okay. We have wave, a phenomena by which we may transfer energy from one point to another without the displacement of matter particle. In wave, we have mainly three different types of wave. One is mechanical wave, second is matter wave, and third is electromagnetic wave. So there are mainly 8 different types of electromagnetic wave, in which in this part we have to define electromagnetic wave having some thermal energy, or electromagnetic wave due to temperature of body. Is it clear?
Yes, sir. So
It is a type of electromagnetic wave. So electromagnetic wave can transfer even through vacuum. So can travel through vacuum also. Electromagnetic wave moves with the speed of light. So you can say it travels with the speed of light. Now in this part, first we have to define Prevost's hypothesis. According to Prevost, every object which having temperature greater than 0 Kelvin will ability to radiate as well as absorb radiation at all time. Since we human being having temperature 37 degrees Celsius, so if you convert it into Kelvin, temperature would be 310 Kelvin, which is greater
yes, sir.
than 0 Kelvin. So we can
Yes.
say even we radiate radiation in our surrounding at all time. Is it clear?
Yes, sir.
So according to Prevost's hypothesis says every object having temperature greater than 0 Kelvin will emit and absorb radiation at all time. According to this theory, we may define why we feel cold in front of ice and why we feel hot in front of fire. Suppose why we feel cold in front of ice, and similarly why we feel hot in front of fire. Suppose there is an individual in front of ice. So according to the Prevost hypothesis, every object will continuously emit and absorb radiation at all time. Since human bird temperature is about 310 Kelvin and temperature of ice will be 273 Kelvin. So according to their temperature, it will radiate more amount of radiation and it will radiate lesser amount of radiation. So net flow of radiation will be from higher temperature body towards
to lower
lower
temperature.
temperature. This net flow of radiation will tend to decrease our body temperature. That's why we feel cold in front of ice. Is it clear?
Okay, so like ice also transmits radiation to us, right?
Yeah. Similarly, in front of fire, body temperature is 310 Kelvin. Let's say temperature of fire is about 100 degrees Celsius. So it will be 373 Kelvin.
Yes, sir.
So there will be more radiation from fire
Fire
towards him
towards
as
towards the
compared to
body.
human body. So there will be net flow of radiation from this hotter body to cold body, due to which temperature of body will tend to increase. So we feel hot in front of it. Is it clear?
Yes, sir.
First, write it down.
Okay, sir. So,
Yes.
like done, certain. Sir, I had one doubt, sir.
Yes.
Sir, like our temperature is more than that of the eye. So, like, why do we feel cold then?
Just see in this part, net flow of radiation will be from our body towards eyes.
Yes, sir.
Is it clear?
Yes, sir.
This net flow of radiation or net flow of thermal energy from our body will tend to decrease the temperature of body,
Yes. Yes. Because it
and
will
we
go.
are
Yeah.
warm blooded.
Yes, sir.
That's why we feel cold. Okay.
Okay. Okay, sir. Yeah.
Now, to define this particular radiation, let me define you some basic term related to this.
So, any other questions related to this? No, they're right.
They will just ask you only these two parts, nothing more.
Okay, sir.
Some important terms. Suppose you have any body placed over flame like this. So we may define three different terms. Suppose this particular radiation is falling on it. So let's say this is Q incident, and some radiation gets reflected back. So there will be QR. Some radiation will get absorbed and some may get transmitted along this direction. So on the basis of amount of incident radiation, we have three different parts: amount of radiation reflected, absorbed, and transmitted. So we may define first absorbance, which is also called absorptive power, and which is also called absorptivity. So it is the ratio of amount of radiation absorbed by the body to the total amount of radiation falling on it. So we can say this is the amount of radiation absorbed by body to the total radiation falling on it. So it is represented by A, which is Q incident by Q total, Q absorbed by Q incident. And since it is a ratio of same quantity, that is heat, so it will be unitless.
It's a stream.
Is it clear?
Yes, sir.
Similarly, we may define reflectance or reflectivity or reflected power. Amount of radiation reflected to the total radiation absorbed incident on it. And third, transmittance. It is the amount of radiation transmitted to the total amount of radiation incident on it.
Okay.
So we have three different parts: absorbed, absorptance, reflectance, and transmittance.
Okay.
So using conservation of energy, we can say using conservation of energy. Q absorbed, Q reflected, and Q transmitted will be equals to total amount of energy incident on it.
Yes, sir.
Now, if you divide this entire part with Qi, you will get Q absorbed divided by Qi.
Yes, sir. Q reflected by Qi, Q transmitted by Qi. Yeah.
Is equals to 1 in right hand side.
Yes, sir.
This particular quantity absorbed by incident is called A. R by incident is called R,
R
and transmitted is
is
equals to
equal
1.
to 1.
Any doubt?
Okay. No, sir.
First, write it down to this part.
Done, sir.
Now, using this part, A plus R plus T, let me define you some term. First is vacuum. For vacuum, there will be no absorbing tendency, no reflecting tendency. So it will transmit maximum. So we can say vacuum is perfect transmitted.
Okay, perfect transmitted.
Next, in case of mirror, where transmittance will be 0,
0
so you're left with A plus R is
is
equals
equal
to
to
1.
1. It is perfect absorber and receiver. There.
In this part, we have A plus R is equals to 1, but for mirror, there will be lesser ability to absorb and more ability to reflect.
Reflect, yeah.
So we can say good reflector
Poor absorb.
or bad absorber or poor
Okay.
absorber.
Okay.
Next is for black body.
So,
There will be no reflectance, no transmittance,
but they can
and
absorb.
absorption will be maximum. So we can say this is
They're
perfect,
perfect
absorber.
absorber.
So from this part, we can say black body is a body which having tendency to absorb all different radiation falling on it. A body which having tendency to absorb all radiation falling on it is called black body. Any doubt?
No, sir.
First write it down.
Done, sir.
Okay. Now there will be two more terms related to this part. First is emissive power. So it is on absorbing radiation when body has acquired some temperature. So on the basis of their thermal energy, it will start radiating or emitting radiation on the basis of their temperature. So we may define emissive power. So it states the amount of radiation emitted by a body per unit area per unit time is called its emissive power. So it is
Amount of energy. Rate.
the amount of
Okay, amount of
radiation
radiation emitted
emitted
per unit
by
area
hot body
by hot body per unit area and per unit time.
is called emissive power.
It's called emissive power.
So emissive power is equals to energy radiated or emitted per unit area per unit
So,
time.
per unit time.
Energy per unit time is also called power. So power of radiation emitted by area.
Area.
And this is also called intensity.
Intensity.
So we may find these different terms related to this emissive power.
Okay, sir.
In it out?
No, sir.
Next, to define this emissive power for any ordinary body with respect to perfectly black body, we may define another term that is called emissivity, denoted by epsilon or small e. It is the ratio of
Radiation absorbed.
emissive power of ordinary body to the emissive power of black body. So it is emissive power of any ordinary body divided by emissive power of black body is equals to emissivity. So it is just a ratio. So we can say it is unitless quantity. Its value would lie in between 0 and 1. And for black body, epsilon will be 1. Is it clear?
Yes, sir.
Okay, first write it down.
Done, sir. Sir, I just had one question. Like that
Yeah.
day, I gave a test like on fluids, mechanical properties of fluids. Sir, did you correct it?
Okay. Tell me the question.
No, sir. Like yesterday, like no, that day I gave a test in the tuition, right? Like mechanical properties of fluids.
Okay.
Yeah. So I just had one question. Like, do you correct the paper or someone else does?
Someone else.
Because I just like wanted if I wrote this like correct answer or something like that. Yeah.
Okay. Tell me the question.
So 1 minute, sir. It's right here. One. So there is written what is the net weight of the body when it falls with terminal velocity through a viscous medium?
Yeah.
I wrote zero, sir.
Yes. This is
Is it?
correct.
It's correct, right?
Yeah.
Answer. I just one more doubt, sir. A balloon filled with helium does not rise in air indefinitely, but it halts after a certain height.
Yeah.
So, like, what's the answer, sir, for that?
On going up, since
Yeah.
density of atmosphere will be not constant throughout.
Yes, sir.
So on reaching a particular level, when density of helium get equated with the density of atmosphere at that point, so both density becomes equal, so terminal velocity of balloon will become zero.
Yes, sir.
So it get halt at that point.
Sir, I wrote like it's due to the when at certain height atmospheric pressure and the inner pressure are at equilibrium, so that so it stops.
It may be the correct answer.
I just had one doubt. That's why.
Okay.
That's it. That's it, sir.
But it will be better to define on the base of terminal velocity, on the base of density of two different interacting body. Okay.
Like sir, at that time I was getting confused, so I just wrote this the pressure difference.
Okay. Now to define these terms, let me define you first Kirchhoff's law of radiation. It states the ratio of emissive power and absorptive power of any ordinary body is equals to emissive power of black body at that temperature. Harsh,
Yes, sir.
according to Kirchhoff's law of radiation, it states emissive power
Emitting
divided by absorptive
absorbing
power
power.
of any ordinary body will be equals to emissive power of black body at that temperature. Is it clear?
So, sir, how do you define ordinary body, sir? Like in for black body, you can define it as a perfect absorber. For ordinary body, what will we write? Like
Any
how
object
do
which is other than black body is considered to be ordinary body.
okay? Other than black object, black body, it's an ordinary body. That's it.
Yeah.
Okay.
So from this part, we can say emissive power of ordinary body equals to emissive power of black body multiplied by absorptive power of ordinary body.
Okay.
Since emissive power of black body will be constant. So this is constant. So we're left with this part and this part. And in this way, we can say these two are directly proportional to each other. So good absorber will be good emitter also. Is it clear?
Yes, sir.
So let me define it. Kirchhoff's law of radiation is say the ratio of emissive power and absorptive power of ordinary body is equals to emissive power of black body
into
at that temperature.
yes at that temperature.
So we can say good absorber are good emitter, but since absorbing tendency is more, so it must be bad reflector, but
A bad
bad.
reflector.
Any doubt?
No, sir.
Now using this concept, we may define numerical part of amount of radiation emitted by any black body. So first write it down, then I'm defining the numerical related to this part.
Done, sir.
Now, to define calculation related to this part, let me define you another concept, that is Stephen's law. According to Provost's hypothesis, it simply explains a hot body will emit and absorb radiation at all time. But how much energy it will radiate or absorb, it is defined by Stephen's law. So it states emissive power of black body is equals to sigma times temperature to the power 4. So from this we can say emissive power is directly proportional to fourth power of their absolute temperature. Is it clear?
Yes, sir.
So according to Stephen's law, it states the amount of energy emitted by black body per unit area per unit time is directly proportional to the fourth power of their absolute temperature. It means emissive power, that is also called intensity, which is also called power upon area. So we may write intensity is equals to emissive power, which is also called energy per unit area per unit time, which is also equals to power per unit area is equals to sigma to the power 4, where sigma is called Stephen's constant, and it is equals to 5.67 into 10 to the power 8 watt per meter square Kelvin to the power 4. This is called Stephen's constant. Is it clear?
Yes, sir.
But this is for any perfectly black body. We may define on the basis of this part. But if you have to rearrange for any ordinary body, we may use Kirchhoff's law of radiation to find relation between black body and ordinary body
Ordinary
according to
body.
emissivity. So first write it down. I'm giving you some problem related to this part.
Yes, sir. Done, sir.
If the black body is at 2 to 7 degrees Celsius and 7 to 7 degrees Celsius, find the ratio of emissive power. If the ratio of their radii is 2:1, find ratio of power. Just use the above formula.
Yes, sir.
Convert temperature into Kelvin first,
Yes,
then
sir.
apply and try to find.
Yes, sir.
Harsh, you got any
Yes.
answer?
So just 1 minute, sir. 1 minute.
Okay.
So what's the answer?
For first part, it will be about 1:16, I think.
Okay. 1:16, yes, sir.
You got the same answer.
Like 1:, like I'm not like that perfect. It's like 1:5. I got 1:14 or something like that. That's what I'm asking.
Just convert this particular temperature into Kelvin. So at first part, you will get 273 plus 227. So it will be 500 Kelvin. Is it clear?
500 and the thousands. It's thousands.
According to the formula, emissive power of first, that is intensity of first divided by intensity of second.
But then
So it will
intensity of
be
second.
sigma T1 to the power 4.
Sigma T2 to the power 4.
Sigma cancel out. So you'll get
Yes,
T1
sir.
by
T1
T2.
by T2 raised to power 4. 500 by 1000 raised to power 4. Like whole raised to power 4. 1 by 2 raised to power 4. Calculation error, sir.
Okay.
I did the same thing, so it's just calculation error.
Okay, no problem. In second part, we have to calculate power. So according to the formula, power is equals to sigma times area T to the power 4. May convert this particular area as area of that black body, pi r squared temperature to the power 4. So P1 divided by P2 will be R1 divided by R2 square T1 divided by T2 to the power 4. So we have R1 divided by R2 is 2:1 to the power 2, and T1 divided by
2:1, 2 by 1, yeah. To the power.
So you will get just 1 by 4. Okay?
Yes, sir. Okay, sir. So I just want to correct my mistake in the first part, sir.
Okay, no problem.
Done, sir.
Okay. Now, the next thing on the basis of this part, we have to define Newton's law of cooling. Before that, let me explain you something. If for any ordinary body, if you have to calculate as emissivity is equals to emissive power of any ordinary body divided by emissive power of black body. We have to calculate emissive power of ordinary body. So we may write emissive power of any ordinary body is equals to epsilon times emissive power of black body, and which is nothing but sigma times temperature to the power 4. So by using this, we may find emissive power, intensity, power radiated, energy emitted by any ordinary body. Harsh, is it clear?
Yeah.
Yes,
sir.
Okay. Now using this
Yes, sir.
concept, now if body is placed in cold surrounding, Suppose this is any hot body having temperature
Sir, you're
T.
lagging.
Just 1 minute. Hello. Is it
Yes,
clear
sir.
now?
Yes, sir. No, sir.
Now, suppose if a body is placed in any cold surrounding, so there will be emission of radiation on either side. This
Yes, sir.
hot
Each
body will
direction.
also emit radiation. It's all side.
Yes.
And the cold
Yes,
surrounding
sir.
in which it is placed will also radiate along this direction. So we have to calculate net flow of radiation in this part. So net intensity will be epsilon sigma temperature to the power 4 of that hot body minus temperature to the power 4 of that cold surrounding.
Cold, cold.
Is it clear?
Yes, sir.
Now we have to calculate amount of heat lost. So we may write this intensity as energy per unit area per unit time. So it will be heat per unit time per unit area is equals to T minus T naught to the power 4. Now move this A to right side. So it will be dq by dt is equals to epsilon A sigma T to the power 4 minus T naught. Now we have to calculate from this part if temperature difference is less than 100 degree. Let delta T is equals to T minus T naught and which is less than 100 degrees Celsius.
Okay.
So T will be T naught plus delta T. Put this part in this, you will get epsilon A sigma. In place of T, we may write T naught plus delta T whole to the power 4 minus T naught to the power 4. Now, epsilon sigma A, if I take out T naught to the power 4 as common, so you'll get 1 plus delta T by T naught to the power 4 minus T naught to the power 4. Further, if we take out T naught to the power 4 common from both parts, and using binomial expansion, you may write 1 plus x to the power n will be equals to 1 plus n times x using binomial expansion. Is it clear?
Yes, sir.
So this 4 will move to its coefficient. So it will become 4 times delta t by t naught minus 1. Now on further simplifying, 1 and 1 will cancel out. Delta t may be written as t minus t naught. So you will get epsilon A sigma T naught to the power Q. Since we have T naught in denominator also, so these two terms will get cancelled out, times 4 delta T, that is T minus T naught, is equals to dq by dt. Is it clear?
Yes, sir.
Now in this part, we have this entire thing constant. And we're left with this part and this part. This is nothing but a rate of heat lost by body when it is placed in cold surrounding. And this is temperature difference of body and surrounding. And this is any constant term. So from this part, we may define Newton's law of cooling. So it states, if a body is kept in cold surrounding, the rate of heat lost by it will be directly proportional to the temperature difference of body and surrounding. Is it clear?
Yes, sir.
First, write it down, then I'm defining you.
So can I scroll down?
Just 1 minute.
Okay, sir. Done, sir.
So from this part, we can say Newton's law of cooling. It states if a hot body is kept in cold surrounding, the rate of heat lost by body is directly proportional to the temperature difference of body and surrounding. So according to the above relation, we may write the rate of heat lost is directly proportional to temperature difference of body and surroundings.
So surroundings.
Since this heat is being lost into surrounding, so it will be negative.
Yes, sir.
Since final heat will be smaller as compared to initial, and there will be constant of proportionality C times T minus T naught, where C will be 4 epsilon A sigma T naught to the power cube.
Constant.
This part.
Yes, sir.
Now, if you rearrange this particular equation, since this dq will be responsible to change the temperature of body, so we may write this dq as a specific heat. Is it clear?
Yes, sir.
As it is responsible to change the temperature of body, so we may write dq equals to ms times dt.
DT.
So dt divided by dt is equals to minus of c divided by m into s times t minus t naught.
So here MSS.
M is mass of body and S is a specific heat constant.
Okay, sir.
I define in calorimetry.
Yes, sir, but I just forgot to use
Okay.
MS.
Now move this T minus T naught to left side and dt to right side. So you will get dt divided by T minus T naught equals to, let's say this entire constant is K times dt. So integrating both sides, 1 by T minus T naught will give you ln T minus T naught is equals to K times T. So if you plot variation of graph related to this part, ln T minus T naught, there will be some initial temperature at this point. So graph related to this part will be a straight line with negative slope. And this particular slope will be nothing but K, which is equals to 4 epsilon A sigma T naught to the power Q by M into S. Is it clear?
Yes, sir.
Now, if you further simplify it, this particular log part, or if you remove this particular log, you will get T minus T naught is equals to exponential K into T. that is exponential function. So graph related to T, let's say this is some initial temperature, so it will be exponentially decreasing with respect to time.
Okay.
Now, for calculation purpose, we may rearrange this particular formula in some different form. So let me define you shortcut method. As we have dt divided by dt is equals to minus of k t minus t naught in the above part. We may write dt as temperature difference T final minus T initial by time difference T minus 0. K, this is called average temperature, that is Ti minus plus Tf by 2 minus T naught temperature of surrounding. Final temperature of body will be smaller as compared to initial. So if you reverse these two parts, you will get T initial minus T final with negative sign. And with negative sign, this negative will get cancelled out. So you're left with this part. Is it clear?
Yes, sir.
First, write it down. Then I'm defining how to calculate numerical related to this part.
Sir, like this is the last part of the chapter.
No, one more thing. Wien's displacement law.
Wien's displacement law.
Yeah.
Okay. So after this, we'll start thermodynamics.
Yeah. In which chapter you are in school?
Sir, we finished thermodynamics, and we are in. We have started this
waves and oscillation and waves.
So we are in kinetic theory of gases, sir.
Okay.
Yeah, kinetic theory of gases. All the portion, like the 2 or 3 pages, like they're studying and you go. So I can scroll a little bit down. Done, sir.
Let me give you a problem related to this part and how to solve. A body at 60 degrees Celsius is placed in surrounding of 10 degrees Celsius. In 5 minutes, its temperature dropped to 40 degrees Celsius. Find time to fall temperature further to 20 degrees Celsius. Let me define you how to solve. First, we have body, which is at 60 degrees Celsius. It becomes 40 degrees Celsius and then 20 degrees Celsius. Time taken from this point to this point is 5 minutes. We have to calculate time duration for this part. If temperature of surrounding is 10 degrees Celsius. Now, we have two different segments. This is first part and this is second part.
Second part.
So in this part, we have T initial is 60 degrees Celsius and T final is
40 degrees Celsius.
40 degrees Celsius and time taken is 5 minutes.
5 minutes.
So use the above formula. So you may write
T initial minus T final by 10.
T initial by minus T final by time taken 5 minutes
5
into
60.
60.
Yeah.
K T initial T final
plus T
divided by 2 minus temperature of
minus 10
surrounding.
degrees Celsius. Yeah.
Similarly, for second part, we may write 40 minus 20 divided by time taken we have to calculate is equals to K temperature Ti plus Tf divided by 2 minus temperature of surrounding. Now you may find K from the first part and put it in second, you will get the value of T. Okay?
Yes, sir.
Just try to solve.
Yes, sir. Sir, I'm getting the value of K as minus 600.
No, it will be plus 600.
It will plus? It will be plus 600.
Yeah.
Sir, like I'm getting like 1 by 600 is equal to K. So I shifted it upwards, so I'm getting minus. Like, is there a.
It
Because
means
I did like, yeah.
you're getting this.
Yeah, I'm getting this.
This is correct. Okay.
This is correct.
Yeah. Just put it in the second part and
So
try to
like I
find
can
T.
keep it like this.
Yeah.
Oh, okay.
Harsh, you got any answer?
Sir, I'm getting 600.
T is equals to 600. Good.
Yes, is that correct?
Yeah.
Okay.
So T is equals to 600 seconds. So if you have to convert into minute, so it will be 10 minutes. Okay.
Yes, sir.
Now, let me define you from this part. Initially, we have body at 60 degrees Celsius. In 5 minutes becomes 40, and further to 20 degrees Celsius, it has taken 10 minutes. 5 minutes to reach from this point to this point, and for this part,
10
it is
minutes.
taking 10 minutes. So just see the amount of change in temperature in this part and amount of change in temperature in this part. Is the change in
It's
temperature
the
in
same,
both
sir.
cases? Yeah, but
Same.
time taken in first part is smaller as compared to second part. Is it clear?
Yes.
So from
Yes.
this we can say, as the temperature of body decreases, so its rate of cooling also decreases. So it will take longer time to change by same amount at lower temperature as compared to higher one. Okay.
Okay. Okay, sir.
So you'll say as temperature of body decreases, the rate of cooling also decreases. So it will take longer time to change temperature by same amount at low temperature.
Okay.
Now from this part, you will be asked, suppose if a body is initially at 100 degrees Celsius and its temperature is decreasing like this. Let's say time duration, this part is T1, and this part is T2, and in this part is T3. So how will T1, T2, and T3 will related with one another?
Over
How will T1, T2, T3 will related with one another? Now just see, we have same temperature difference in all different parts.
yes, sir. -10.
So using the above concept, as the temperature of body decreases, so it will take longer time to change by same amount of temperature. Is it clear?
Okay, okay, yeah, yes, sir.
So we can say T3 will be maximum, T1 will be minimum. So
Okay,
relation will
yeah,
be T1.
T1. Okay, how are the related? Yes,
Is it clear?
yes, sir.
Okay, just write it down.